Mind-bending illusions. Explained, the science behind what you see. Have you ever seen something that just didn't seem quite right? Something that made you question what you were actually looking at? That's the power of visual illusions. Illusions are more than just fun tricks. They reveal a fundamental truth. Our perception is a construction, not a perfect reflection of reality. Illusions are fascinating because they trick our brains into seeing things that aren't really there, or seeing things differently than they actually are. It's like a magic show for your mind. Our brains are incredible processors, constantly working to make sense of the world around us. But even these amazing machines are prone to taking shortcuts and making assumptions, which can lead to some truly mind-bending illusions. So, how do these illusions actually work? Let's take a peek behind the curtain and explore the science behind our visual system. It all starts with light. Light enters the eye and is processed by the retina, a layer of tissue at the back of the eye that contains light-sensitive cells. These cells convert light into electrical signals, which are then sent to the visual cortex, the part of the brain responsible for processing visual information. The visual cortex doesn't just passively receive information. It actively interprets it, using pre-existing knowledge, memories, and expectations to make sense of what we're seeing. Our brains are masters at recognizing patterns and using context to fill in gaps. This helps us quickly understand the world around us, but it can also lead to illusions. Illusions arise from this interpretive process. They highlight the assumptions and shortcuts our brains take when processing visual information. Let's dive into some specific examples, starting with geometric illusions. These illusions involve the distortion of lines, shapes, and sizes. One of the most famous geometric illusions is the Müller-Lyer illusion. Take a look at two lines of equal length. One line has arrowheads pointing inward at each end, while the other has arrowheads pointing outward. Even though the lines are the same length, the one with the inward pointing arrowheads appears shorter. Why does this happen? It's believed that the arrowheads at the ends cause perceived depth differences. Our brains interpret the inward-pointing arrowheads as representing the corner of a room, which appears closer. Conversely, the outward-pointing arrowheads are interpreted as the corner of a building, which appears further away. Another classic example is the Ponzo illusion. Imagine two identical objects placed on top of two converging lines. The object placed higher up in the image between the converging lines appears larger than the object placed lower down. This illusion works because the converging lines create a sense of depth, similar to railroad tracks receding into the distance. Our brains interpret the object higher up as being further away. To compensate for the perceived distance, our brains make the object appear larger. Now, let's explore color and brightness illusions. These illusions demonstrate how our perception of color and brightness is heavily influenced by context. Consider the checker shadow illusion. This illusion features a checkerboard pattern with two squares labeled A and B. These two squares are actually the exact same shade of gray. However, square B appears much lighter than square A. The surrounding context influences our perception. Square B appears to be in shadow, while square A is in direct light. Our brains use relative brightness to perceive color. We don't see absolute values, but rather how colors compare to their surroundings. Our brains assume that objects in shadow are darker than they actually are. This is because shadows reduce the amount of light reflected from an object. To compensate for the perceived shadow, our brains adjust our perception of square B, making it appear lighter than it actually is. This illusion highlights the brain's reliance on context when interpreting visual information. It shows that what we see is not just based on the raw data from our eyes, but also on our brain's interpretation of that data. Finally, let's explore motion illusions. These illusions create the perception of movement from static images. One striking example is the rotating snakes illusion. This image consists of a pattern of colorful shapes arranged in a circular fashion. When you look at the image, it appears to be rotating, even though it's completely static. The snakes seem to be slithering around in circles. The exact cause of this illusion is still debated, but it's attributed to how our brains process color and contrast. The specific arrangement of colors and shapes leads to a perceived shift in position, creating the illusion of movement. Another interesting example is the autokinetic effect. In a completely dark room, if you stare at a stationary point of light, it will appear to move. This happens because your eyes are constantly making small, involuntary movements. In the absence of any other visual references, your brain struggles to stabilize the image. Your eyes drift, and your brain tries to find a reference point to anchor the light. This leads to the perception that the light is moving. Illusions are more than just entertaining tricks. They provide valuable insights into how our brains function and how we perceive the world around us. Illusions demonstrate that perception is an active, not passive process. Our brains are constantly interpreting and constructing reality based on the information they receive. Our brains work tirelessly to create a coherent and meaningful experience. They fill in gaps, make assumptions, and use context to make sense of the world. Studying illusions helps us understand how we see, how we learn, and how we make decisions. It sheds light on the complex processes that underlie our everyday experiences. Illusions remind us that what we see isn't always what's there. Our perception is subjective and can be easily influenced by a variety of factors. By understanding how illusions work, we can gain a deeper appreciation for the incredible power and complexity of the human brain. We can also become more aware of the potential for our perceptions to be distorted, leading to a more critical and nuanced understanding of the world around us.